All right, welcome back, everybody. We're going to talk about properties of similar triangles today. We have three theorems, which we're going to prove all of them, and then three examples to go with those theorems. These theorems are challenging, I have to be honest with you. So buckle up and let's get started. The first theorem is the triangle proportionality theorem. We'll read that and then we're going to prove that. The triangle proportionality theorem says that a line parallel to one side of a triangle divides the other two sides proportionally. So if you look at this drawing I have here, we have a triangle ABC and then a line that's parallel to one side. So we're trying to prove that the two sides that are intersected by that line are divided proportionally. So we're trying to prove that AE divided by EB, so the left side, the two pieces of the left side, that ratio will be equal to AF divided by FC. Okay, so there's your drawing. So I've outlined the key steps here. We're going to, first of all, claim that triangle AEF here on the top, the small triangle, is similar to triangle ABC, the big triangle, by angle. And you can see that by these two angles being congruent. Those are corresponding angles. Parallel lines cut by transversal corresponding angles are congruent. And also by these two, or actually you could just say they share a common angle. But by angle, the small triangle and the big triangle are similar. Okay, so I'm going to start out by saying that segment AB, which is the left side of the big triangle here, I have to move back and forth, but segment AB, the left side of the big triangle, divided by AE. Those are corresponding sides of the two triangles. That ratio then would be equal to AC, which is the right side of the big triangle here, divided by AF. Those would be the right sides of right sides of similar triangles. So they're corresponding sides of similar triangles, so they're in the same ratio as the other pair. So we have this statement here. So AB divided by AE equals AC divided by AF. Gets a little tricky here. I'm going to write AB here as a sum of two segments. So I'm going to say that AE plus EB is equal to AB. And to see that, just look up at the drawing again. So I'm just saying that AE, this piece, plus EB, these two pieces add up to the total AB. And then that's the same thing here on the other fraction. AF plus FC adds up to AC, and you can see that by just looking at the diagram. AF plus FC is equal to AC, just the segment addition postulate. Okay, then these denominators here are just the same as the step above. Then what I did here is I broke up these two fractions into two each. So I just rewrote the left side as two fractions, and I rewrote the right side as two fractions. Just property of fractions there. And then notice that this number, this fraction I should say, is equal to 1 because it's AE divided by AE. And this fraction is equal to 1 because it's AF divided by AF. And so those can both be subtracted from the equation because you're subtracting 1 from both sides. And so you end up with just EB divided by AE equals FC divided by AF after you subtract out those two ones. Then if you just flip over this fraction, we talked about a property of proportions. You flip over these two fractions, so you got AE divided by EB equals AF divided by FC. So that's what we're trying to prove. So if we look back up at the drawing, that'll reinforce that. So we just proved that this line, which is parallel to that third side of the triangle, intersects these other two sides proportionally. So AE divided by EB equals AF divided by FC. So just like you're going to see today, the theorem is worse than the problems, but that's where the theorem comes from. Okay, let's do an example using that. You see the example is not that bad. So we've got a line parallel to one side of a triangle. You see line XY parallel to side BC in that triangle. So the triangle proportionality theorem just says that parallel line divides the two sides proportionally. So we're going to write a proportion. So these two parts of the one side, so 4 divided by 9, there's your ratio there, would be equal to this piece, which we called CY divided by 10. So just those other two sides got divided proportionally. So we just take that proportion and cross multiply. So we got 9 times cy equals 40, and then cy equals 40 divided by 9. So there you go. We just found that segment cy right there by the triangle proportionality theorem. Okay. Okay. Next one. These theorems are kind of mean. This next one is called the two transversal proportionality theorem. So now, earlier in the year, we had two parallel lines cut by transversal. Now we have three parallel lines cut by two transversals. Okay, so here's what this two transversal proportionality theorem says. If three parallel lines are cut by two transversals, then the transversals are divided proportionally. So if we look at the diagram, there's your three parallel lines we've seen by the three red arrows. You see the two transversals. We're trying to prove that AC, on this first transversal, this piece AC divided by CE, those two pieces, those two segments, that ratio would be the same ratio as BD divided by DF. Okay, so in other words, these two transversals get divided into the same ratio by those three parallel lines. Okay, so what I'm going to do to prove that is draw a line here through E and B. Like that. Okay, now, if you look at this one triangle here that we made, and then we're going to focus on a different one, but just looking at that one right now, we have the triangle proportionality theorem here. We can say that AC divided by CE, that's the two pieces of that triangle, equals BX. Oh, sorry, let me get that X in there. That's an X. BX divided by XE. So notice that line parallel to one side of the triangle divides the other two sides of the triangle proportional. We just had the triangle proportionality theorem. And that's where we get this proportion right here. Okay, now, we got that step. Now let's erase that yellow triangle and draw a new one. Now let's look at this triangle. Same theorem here. We got this line CD parallel to EF, this side of the yellow triangle. So now we can say that BX divided by XE, I'm looking at this proportion right down here at the bottom, BX divided by XE equals BD divided by DF. Again, that's the triangle proportionality theorem applied to a different triangle, the yellow one now. So we got that. Now, if you look at those two statements taken together, you got the transitive property, right? Because this fraction and this fraction, these are the same. So I got the first fraction equal to BX over XE. That BX over XE is then equal to this fraction. So the first fraction, so when we started with this one, must be equal to the last one. So AC divided by CE is equal to BD divided by DF. And if you go back and look at what we were trying to prove, that's exactly what we were trying to prove. So long story short, you got three parallel lines cut by two transversals. We just proved that AC, this first transversal, it's two parts, AC divided by CE, equals the two parts of the other transversal, BD divided by DF. And that's what we just proved right there. So that's the theorem we just proved, which is called the two transversal proportionality theorem. Again, it's easier to use than it is to prove. So let me do an example for that one. Okay, so here you see we got to find X. This one's a little bit cleaner here. And you see three parallel lines cut by two transversals. And what that theorem just told you was that those two transversals got divided proportionally. So we're just going to take that first transversal and write a fraction from it. We can write our blank proportion. So X over 12, those are the two pieces of that first transversal. That fraction is going to be equal to the two pieces of the other transversal. So x over 12 equals 6 divided by 8. Now, as we've talked about before, before you cross multiply, you can reduce that fraction to 3/4. So then cross multiply. So 4x equals 36, and x equals 9. So again, the problem, not as bad as proving the theorem. Okay, so I got to mentally prepare you for this last one. This last one is really difficult. The proof is just amazingly difficult. So I'll go through that proof and explain the best I can, then we'll do an example with it, and then that'll wrap it up. Okay, so our third theorem and last theorem of the video is the triangle angle bisector theorem. And we do have problems on this, by the way, so hang in there. The triangle angle bisector theorem says an angle bisector of a triangle divides the opposite side into two segments whose lengths are proportional to the lengths of the other two sides. Okay, so let me show you what I'm talking about with this diagram, and then I got to go to work. So you see triangle FDE, the big triangle. This is an angle bisector. You can see segment DG bisects angle FDE into two angles which are congruent. That's what an angle bisector does. And we call them angles 1 and 2. So we're given angles 1 and 2, really. So the theorem says that the opposite side, so FE, is broken into two segments, FG and GE. You see that in our first fraction, which are proportional to the other two sides of the triangle. So we're trying to prove that segment FG divided by segment GE, the two pieces of the third side, are in the same ratio as FD and DE. That's what you see right there. Okay, so this is going to be a challenge. So what I'm going to do is I'm going to draw. I got the instructions here, note to self. I'm going to do these two things first, and then we'll go through the proof. So I'm going to draw a segment EK. You don't see K yet, but I'm going to put it up there. You can draw a segment EK parallel to GD. So from point E, I'm going to draw that line parallel to GD there. Best I can. Okay, then I'm going to extend side FD. So FD, you can see right there, I'm going to extend that side down to meet. Almost did it. I'll cheat a little bit there. Okay, so that's the point where they meet is point K. So keep in mind that these two segments here are parallel because I drew it that way. Okay, so I'm going to put some numbers in here. So this is going to be angle 3, and this is going to be angle 4. Now, look in my proof here. These are just kind of notes, really, instead of a 2-column proof. Angle 1 is congruent to angle 3. So you see, hopefully, this letter Z here. And so when you have the letter Z, you got two parallel lines cut by transversal. Angles 1 and 3 are congruent because alternate interior angles are congruent. So angles 1 and 3 are congruent. Let's keep that in mind. 2 and 4 are also congruent. So angle 2 and angle 4 down there are congruent because this time you got corresponding angles are congruent. So here's your parallel lines. There's your transversal. And angles 2 and 4 are corresponding angles, both on the same side of the transversal, both above the parallel line. So that's how we got angle 2 congruent to angle 4. Okay, now look at this. We got angle 1 congruent to angle 3, angle 2 congruent to angle 4. Remember, back up at the beginning, we had angles 1 and 2 congruent. So angles 3 and 4 are congruent to congruent angles, so that makes them congruent to each other. Okay, let me say it again. Angles 3 and 4 are congruent to congruent angles, so that makes them congruent to each other. So we can conclude that angle 3 is congruent to angle 4 down here. I can go ahead and mark those. Angle 3 congruent to angle 4. Now, because of, if you look at triangle DKE now, that one right down there where the pointer is, now I can say that this segment DE is congruent to DK. That's the converse of the isosceles triangle theorem. If two angles of a triangle are congruent, then the sides opposite those angles are congruent. So there we got DE congruent to DK. We're going to need that here in a minute. Okay, now let's look at this proportion, FG over GE, and look at what we're looking at, FG over GE. That's these two segments right here. That ratio is the same as FD over DK. FD over DK. That's a triangle proportionality theorem, the first one we had today. Line parallel to one side of a triangle divides the other two sides proportionally. So that's a triangle proportionality theorem. Now we make one more substitution and we have what we're trying to prove. And I outlined that in green here. So remember when we said that right here that DE and DK were equal? Just replace that DK with DE in this proportion right here. It's the same exact proportion, just with DK got replaced by DE. So now we have, let's read it and then we'll look at the diagram. FG divided by GE equals FD divided by DE. So if we look back at the drawing here, I'll repeat that. FG divided by GE, these two pieces of that side opposite the angle that got bisected, is equal to FD divided by DE. So that's the other two sides of the triangle. Okay, so we'll do it. We'll do a triangle. Oh, sorry, we'll do an example with that theorem, and then wrap it up. But again, it's just like before. The problem is not as bad as the theorem. Okay, so here's what we got to do in this last example. You see triangle RST, and you see that I bisected angle S there. So we got an angle bisector. And the triangle angle bisector theorem says the opposite side is divided into the same ratio as the other two sides of the triangle. So I'm going to set up an empty proportion. So these two sides that are opposite the bisected angle are x plus 2 and 2x plus 1. So they make up one fraction. That side opposite the bisected angle is divided into the same ratio, which I have there, as the other two sides of the triangle, which is a 10 and a 14. All right, so all we have to do is solve that for x, and then once we find x, we'll go back and plug it in and get these two line segments here. Hang in there, almost done. All right, so we got x plus 2 divided by 2x plus 1 equals 5 over 7, just reducing the fraction. Let's go ahead and cross multiply. Let's go 7 times x plus 2 equals 5 times 2x plus 1. Let's do the algebra. So 7x plus 14 is 10x plus 5. 14 is equal to 3x plus 5. Subtract 5. So 9 is equal to 3x. X is 3. Okay, we're not done yet, right? Because we got to go back and find these segments that they wanted. So they wanted RV. So RV is right here, so that's x plus 2. So we said x was 3, so 3 plus 2. So that piece is 5 right there. And they wanted VT, so we said x is 3 again, so that was 2 times 3 plus 1, that's 7. So that piece is 7. So there you go. You can see it right there, 5 over 7 equals 10 over 14. Okay, that was a lot. That was a lot. We had 3 difficult theorems to prove, and but they do result in examples or in types of problems that really we can pretty easily solve. But let me recap the theorems to bring them back, and then we'll give you some practice. The first theorem today was a triangle proportionality theorem. It said if a line is parallel to one side of a triangle, then it divides the other two sides proportionally. All right, then we had the two transversal proportionality theorem, which says if 3 parallel lines are cut by 2 transversals, then the transversals are divided proportionally. So again, if three parallel lines are cut by two transversals, then the transversals are divided proportionally. And then our last theorem we had today was the triangle angle bisector theorem. And that one just says that an angle bisector of a triangle divides the opposite side into two segments whose lengths are proportional to the other two sides of the triangle. So there you go. All right, good luck with that. Let's do some practice problems.